right, so we are here again with set number 2. So if you watched the first video that I made, it was terrible and you couldn't really see anything. And so we're going to try something new. I hope this works better, but I guess we'll see. So let's start on set 2. Starting with set 2, we have dimensional analysis. So we are given M with dimension M box or M bracket, X to L, B to L over T, A to L over T squared, T to big T. Okay, so it doesn't take much to figure out that M is meter maybe, or mass, depending on what they're calling M. X is probably L for length. V is L for length over T. A acceleration is L over T squared. And T goes to T. So T is probably time, L is probably meters. The big M, I would guess, is probably mass. So it doesn't matter what they are. We're going to just use dimensional analysis to figure out some problems. So you will notice if you get into any upper level physics classes, dimensional analysis is really a really good tool to use at times. If you have this huge equation and you think you did it right, but you're not exactly sure, you can look at the dimensions and say, okay, does that make sense? I got an answer for, I don't know, let's say acceleration. Did I get an acceleration that is a length over a time squared? Actually, really a good tool. Okay, so moving on, let's just solve some problems. So let's look at number 1. We have, if there is a variable K and it has dimensions big M times L squared over, that's ugly, I don't like it, over T, L squared T squared. What should the dimensions of little k be in the equation big K equals little k M B squared? All right, so let's plug in for K. We have M L squared T squared equals little k, which we're trying to figure out. M we're given above, big M, and B squared we're given above, which is L over T. And in our equation here, we see that V is squared, so we're going to square this. So let's take a look here what we've got. On both sides, we can cancel what we have on both sides. So we can see that we have 2 M's, so we can cancel those. And we see that we have, if we take the bracket away and we move it inside, we're going to have that. We can cancel L. Okay, and we can also cancel the T. So what does that mean? We're left with nothing on the left-hand side. So what that means is K, little k, is dimensionless. So what is something that would be dimensionless? If you were going to say, Jim ran at the velocity of 2 meters per second. Kim ran 2 times Jim's rate. That 2 would be like the K. The 2 is dimensionless. You're just doubling something. So K is dimensionless, maybe like a constant in the example that I gave. Okay, so let's move on to a little more complex problem 2. What should C1 and C2 be in the expression V equals C1 e to the negative C2t. Okay, this is one's a little bit more complex, but what we know for sure is that what's on the right-hand side has to match what's on the left-hand side. So it doesn't make sense to have a velocity that's measured in meters per second on one side, and on the right-hand side, we have meters that they have to match, just like the numbers on two sides of an equation have to match. So 2 doesn't equal 4. We have to have the same dimension. So we know for sure that this is going to have to be what V is. And we know that V is L over T. All right, so we have 2 variables on one side. So how are we going to figure this out? Well, we want the variables in the exponent to go away. We want e to the something. That's something, we just want to be a constant. We want it to be a dimensionless constant. So in that we have C2 times T. We want dimensions to be dimensionless. Okay, so how are we going to do that? Well, we know that the dimensions for T are big T. So if our dimensions for T are big T, and we want it to go away, we need to divide it by T, or we could say C2 is 1 over big T. All right, so we figured out what C2 is. Now we need to figure out what C1 is. So if E just becomes a constant, then C1 has to equal V. And we got V is L over T. So C1 must be L over T, and that's our answer. C1 is L over T. C2 is, 1 over T. There we go. All right, so let's do 3. Okay, so like we said before, we need the dimensions on the right-hand side to match the dimensions on the left-hand side. So how will we do this? Let's start with the omega t. So now again, just like the exponent, we want the expression in the brackets or the parentheses, the omega 2, to go away. We want it to be sine of a constant. So we have T goes to T. So omega, again, then, just like in the exponent, is going to have to be 1 over big T. All right, so then omega t goes away and becomes dimensionless, which is what we're looking for. So then we are left with x equals a1 plus a2 times a dimensionless constant. Doesn't make sense to add 2 numbers together that don't have the same dimensions. So you can't add x equals 2 inches plus 3 meters per second squared. That doesn't really make any sense. So A1 is going to have to equal A2 is going to have to equal X. So we know that X is measurement of length. So then A1 must be length. And a 2 then must also be length. So what we get is omega goes to 1 over t. And there's our answer. So let's look at number 5. Certain physical quantity R, using the formula R equals 4 a squared over b minus c, where a, b, and c are lengths. What is the SI unit for R? What is the standard unit for R? So the standard unit for R is something that you can just Google when we're done figuring out what the SI unit is for R. But let's plug in what we know to figure out what R is a measure of. So whenever we're doing dimensional analysis, we just get rid of the constants because they are dimensionless, so we don't really care about them. So 4 can just go away. So we are left with a squared over b minus c. So if a, b, and c are all lengths, we can say x goes to L, as we're just kind of assuming that L is saying a dimension of length. So we can say that B goes to L, A also has a dimension of L, and C has a dimension of L. So let's plug those L's into our equation. Of course, getting rid of the 4 because that's a dimensionless constant. So if we have a squared, we're going to have L squared. And if we have B minus C, those have to be the same dimensions. So, oops, we're going to have L. We can cross off 1 from the bottom, cross off the 1 in the bottom, cross off 1 from the top, and we are left with a dimension of L. So we have R is the dimension of L. What is the SI unit for L? Length. That is going to be meters. You might see kilometers sometimes, but the SI unit is meters. So what is the standard unit? Another unit for standard is English unit, common unit, I think sometimes it's called. It's what we use when the rest of the world uses metric. So the SI unit for R, there isn't, or the standard, I'm sorry, standard unit for R, there isn't one. There's inches, there's feet, there's yards, there's miles. If we want to match the closest to meters, we would probably say yard. So we would say the standard unit for R would be yard. But this is a physics class, so we're not going to use that. We're going to use meters. All right, so let's move on to a little vector analysis. Fun stuff. So as I'm sure you have seen watching our professor's videos, when you were adding a vector, let's say our vectors are this and I don't know, this. To add a vector, you are going to draw, you're going to come up with an origin. For our purposes, we're just going to have origin at 0. 0, 0 is going to be our origin. So if we draw a, let's do a different color. So if we draw A as our vector, we're going to add B to A. And the way that we're going to do that is we're going to go to where A ended, and we're going to take B from here where it starts, and we're going to lay it right here where A ends. So plus B is going to look like that. So then if we were looking to find what A plus B is, we're going to start at the origin, and we're going to draw a vector, and we're going to figure out what that is. Quick explanation. So let's actually go to the problems then. Go back to black. All right, consider 2 vectors A and B, which are shown. A looks about like that. B looks about like that. kind of the exact opposite of what I drew. And we're looking for the difference. So A minus B is represented by which figure? So this can be done a few different ways. I looked in your book, and the way that your book says to subtract a vector is to basically flip B. So what we're going to do is we are going to, before we start really drawing out our problem, we're going to take B and we're going to draw it as we would need B plus to be negative to be 0, or basically flip it. So if this is our B, and we just kind of draw here a y-axis, if we flip B, we're going to get this. Now, as you can see, if I were to make this vector like this, and I were to add negative B to it, so we're going to start right here, we're going to add negative B, we're going to go like this, and we're going to end up right back at the origin, or we're going to end up at 0. So negative B looks like what you see up above here, where we're going to draw our problem. So now we're going to add A to, or we're going to add negative B to A. 4 vectors, how you add them is very important. The order of addition is important. So again, we're going to draw our little graph Cartesian coordinate set here. We're going to take an A. We're going to start with A because it's A minus B. So let's just draw A like here. And then we are going to add a negative B. Make sure I'm looking at the problem here. All right, so we've got A, and we're going to add the negative B, like so. And then we're going to draw a line. Actually, let's do negative B as black. All right, so then we are going to draw a line from where we ended to the origin. And we get, let's call it C, and we get C. So looking at what our problems look like, A, B, C, and D, we can see that A is obviously not correct. That's a straight line down, and straight line down is going to take us, it's going to take us to an axis, but it's not going to take us to the origin. And if we look at D, D looks like maybe, D looks like maybe if we were to add A and B together. So that's going to be out. So then we're left with B and C. And our correct answer is going to be C, because our line goes from our origin to our ending point. So now we're going to use the same A, B, and C. And we're going to switch the order, and we're going to look how order is very important when we add vectors. So we're going to start with flipping A. So if we to draw another little generic Cartesian coordinate graph, we're going to look at A, and A looks like this. Now we want to basically flip A so that adding A to negative A together is going to get us back to the origin. So if this is A, we're going to make negative A look like that. So if we were to add A to negative A, we would get A, you end here, you're going to add a negative, you're going to go like this, and we're going to be back at the origin. So let's go ahead and do what the problem asks us to do, which is B minus A this time. I want back. Okay. B minus A instead of A minus B, which is up here. Okay, so B minus A, we're gonna look at B, and B looks like this. This is B. And negative A looks like this. Maybe more like that. All right, so if we again are going to draw a line from the origin to where we ended, our answer, C, is going to look like this. And if we again look at what we're given, it's A is out, D again is out. We said that C was the answer to 6. And if you look, it's basically just flipped over. So our 7 is going to be B. So our answer for this is B. Our answer for above 6 is C. All right, so moving along to 8. The angle between vectors A and B is 30, and their sum is C. Which of the vector diagrams correctly describe the vectors A, B, and C? Okay, so we know that the angle between vectors A and B is going to be 30. So let's find one where the angle between those two vectors is 30. So A and B, so the angle between A and B of 2 is 150, so that one's out. The angle between, if we add A to B, %30 between A and B, so 1 could be an answer. So the angle between A and B and 3 is 30%. 3 could be an answer. Number 4, if we were to take the angle between A and B, we are not going to get the angle that they've drawn. We're going to get the angle. So if I were to draw it quick, the angle between A and B, even though there's a vector in between here, that's going to be this. And if a flat line is 180 degrees, we can actually figure out what that angle is by how they put 30 in here. So if it's going to equal, these two angles have to equal 180. 180 minus 30 going to give us 150. So number 4, the angle between A and B is 150. And for 5, the angle between A and B is not 30. It looks like that's 90. The angle between A and C is 30, and so 5 is out. So only 1 and 3 can be an answer. So let's look at which is the right answer. So it says that we're going to get C by adding A to B. And we know adding A to B, we take A, looks like factor A always looks like this. We're going to add B to it. So whatever our B is going to look like, if it looks like this or this or this or this, it has to start where our ending of A is. So if A is this one, that would be adding A to B. If it looks like this, that would be adding A to B. If it looks like this, that is not adding A to B. This one, A would have to look like that. So for sure, 3 is out. This cannot be adding A to B. This would be adding A to B, but it doesn't look like that. So 4 for sure is out. And 5, A, B, this is adding A to B. So the only ones that could potentially give us an answer where we're adding A to B would be 5, would be 1, and would be 2. Well, we already said if we're looking at the angle between A and B is 30, that only 1 and 3 can be the correct answer. So if 3 can't be the addition between A and B, 1 must be the correct answer. So one is the correct answer. All right, so that is set 2. I will be uploading this video soon, and I will see you on the next one.